chapter's topics do you want to start with?
25, 26.
25, 26, yes.
25 is
Heterocycles?
heterocycles, yeah.
Let me look at
Amino.
my quizzes.
Yep.
I will say that this semester he's definitely been pulling more from his notes, like practical applications or real world scenarios. So we can definitely go over Dr. Cosper's notes to kind of get a general idea of what's going on. But I know he's definitely had more quiz questions that haven't been represented in her notes, so I would just keep that in mind when you're studying. Okay, so chapter 25, heterocycles. So what is the definition of a heterocycle?
Cyclic structures.
And?
They're cyclic.
S-O-N.
Good, so one of the carbons has been replaced with either sulfur, nitrogen, oxygen. Okay. You can have regular cycloalkanes, but you can also have aromatic, okay? You'll notice that a lot of the front page goes over your cycloalkane heterocycles, but really when you start looking into the next page, we're talking all about aromatic. So all of the actual reactions that you talk about in this chapter are all regarding aromatic heterocycles. Now, I think there was a question on the quiz, something along the lines that it was asking about either EAS or NAS, but it was referring to, I think it was oxycyclopentane, something like that. And it was asking if that would undergo EAS or NAS. All of your conversations about EAS and NAS have been about aromatic, okay? So it's not going to, you're not going to worry about those reactions if you're just talking about a cycloalkane heterocycle. Okay?
So those will usually be like, name this, stuff like that.
Yeah, exactly. Or draw a structure, something along those lines.
Can you go over how to find, in like the furan, the pyrrole, and the diaphene, how to find how many pi electrons it has?
Yeah, and we'll go back to chapter 15 for that, because chapter 15 has a good review.
Because I know they have the lone pairs, but I didn't think that that contributed to the Huckel's rule.
Okay, it will, and let's talk about that. So aromatic. Okay, so let's see. Okay, so when we're looking at pi electrons, it's really easy to see in benzene, right? Because we've kind of been trained to see a double bond has one pi bond, meaning it has 2 pi electrons. So it's really easy to count those, right? 2, 4, 6, which we know is a Huckel's rule, okay? Now, the reason that we count those, oh geez, this is gonna annoy me. Remember that we're really talking about pi systems that are being connected. So that's what we're really talking about, okay? So 2 pi electrons is going to connect, a pi system, and we're seeing that connected throughout the cyclic compound. So if we look at something like this, we know that we have pi electrons here. Now, one of these lone pairs of pi electrons is also going to fit in that p orbital and connect the dots there in a sense. This other set of pi electrons is going to be in a p orbital, but it's going to be in a different plane. Okay, so remember there are 3 p orbitals. One's vertical, one's horizontal, and one's basically coming out at you, okay? So we're focusing on the fact that we have a vertical p orbital that's going to allow for electron movement throughout. Okay, so if you see something like this, okay, we know that we have 2 4-pi electrons here, but you also need to know that nitrogen has a lone pair of electrons. So 2, 4, 6. Okay. Trying to think. Let's do some other examples.
So is the N in Huckel's rule, like the number of cyclic, like the number of rings?
So this is where it gets tricky, and okay. So what is Huckel's rule?
4N plus 2.
Okay. So this N doesn't correspond to something in the molecules. Okay, you're not looking for something here to plug in as N. You're looking to see, does the number of pi electrons match a given number given by that formula? So for example, okay, so if we plugged in 1 for N, what would it be?
6.
We did 2, 3, okay, you probably won't see more than that. So I just plugged in random numbers that gave me the aromatic, the Huckel's rule numbers. So I didn't, it doesn't correspond to the number of double bonds, the number of, this N doesn't correspond to anything within an actual molecule. You're taking these numbers and identifying whether these molecules have those number of pi electrons. It's annoying.
Okay. So
Um,
he's never going to ask us to solve for N. Like, what is N?
No, because N is just an integer. That's all it is.
That's what I was like. I don't even know how to find N.
That's all it is.
Okay.
You don't find N. N is just a random number, and if this number corresponds to the number of pi electrons, you have an aromatic.
Okay.
Yep.
That I get. Okay.
Yep. Okay. So if we have something like this, how many pi electrons are there?
8.
8. So we have 2, 4, 6, 8. Would this be aromatic, non-aromatic, anti-aromatic?
Anti-aromatic.
Anti-aromatic, good. What if we had...
And what makes it anti versus non?
Yeah.
Anybody remember?
That's isn't it when the double and single bonds are alternating?
So I think I know what you're saying, but let's just be a little bit clear. So it has to do with the number of pi electrons.
Right.
So if we had just 4N, so we do 4, 8, 12. Okay. So with this, we have alternating. So we do have delocalized pi systems, but we don't have the correct number of pi electrons. Okay. Anti-aromatic is when there's 4N. Non-aromatic is when we have something like so we don't have a pi system. We don't have a connected pi system. Okay, so even though we only have 4N pi electrons, because it's not an interconnected system, this would be considered non-aromatic. Basically, you just don't have a roadmap, right? So we haven't connected all the dots. So it doesn't matter how many pi electrons we actually have because we're not connecting the dots.
Okay.
Here we're connecting the dots, but it's an unstable amount of pi electrons. This has both, so it's aromatic.
Okay.
This is a confusing topic in general. Let's see. In terms of questions on chapter 25, I don't think he'll get that picky. Did he have any questions where he asked you if something was aromatic or not? For chapter 25?
No.
Okay, back in chapter 15,
Yeah.
yes. Yeah. So you will need to know that for the final, but I don't think he has very many questions on chapter 15, if I'm correct.
He told us he was going to have 6, but
So if it is 6, that's pretty minor, right? Because there's, what, 120 questions, something
Yeah.
like that?
Bit 13.
So that is how you find out if something is aromatic or non-aromatic or anti-aromatic. Again, more about chapter 15, but definitely good information to know. With naming, how would we name this?
Azacyclopropane.
Good. What if I changed it to a sulfur?
Yeah, cyclotron.
Good. Okay. Not too bad naming those, right? Those are usually pretty gimme ones. Okay. So the larger part of this chapter has to do with the actual reactions. Okay. I'm going to skip around a little bit from what Dr. Cosper has in her notes. So let's talk about Pyrrol. Okay, so we've got aromatic with, it's a heterocyclopentadiene. I would be comfortable with that term. He might just use that instead of Pyrrol. So heterocycle pentadiene. Okay. So we have protonation and deprotonation of this. Okay. So when we're talking about protonation, okay, essentially we're going to add a hydrogen to one of these other carbons. Okay, and that's going to offset the electrons here. I would note that this really only happens with a very, very strong acid. Okay, so this doesn't readily happen. But when it does, we're going to lose our hydrogen here, and we're going to shift our double bond. So our double bond is going to go here, and it's going to go here. Okay, so protonation of Pyrrol, we're going to add a hydrogen to one of the carbons in the ring system. Only occurs with a very strong acid, and the electrons need to shift to delocalize that positive charge that's going to end up on our nitrogen. Okay, so that's protonation. On the other side, we have deprotonation. So this is going to happen much more readily than protonation, okay? And we're going to deprotonate the nitrogen. So protonation occurs on the carbons. Deprotonation, we're going to pull off this hydrogen here. So what we're going to be left with we're going to have the electrons from removing this hydrogen. And that's really stabilized by electron delocalization. So resonance is going to stabilize this, which is why this process happens much more readily than protonation. Okay? So deprotonation, we're removing a proton from the nitrogen, and this is going to be stabilized by resonance. Okay? Any questions about these two? Okay. So now we're going to talk about electrophilic aromatic substitution and nucleophilic aromatic substitution. For EAS, we're going to talk about two different ones. So we're going to talk about Pyrrol and we're going to talk about Pyridine. So Pyrrol, and with all of these, you should know how readily it happens and where the substitution would take place on the ring. Okay, those are two big important ones. So with heterocycle pentadienes, I have it as aza. I have it as Pyrrol, but this could be with oxygen or with sulfur. The sites are going to be the same either way. Okay, so this is one that could lend itself to drawing arrows like this, or he could ask you, which carbons on the Pyrrol ring will undergo EAS. So carbons 2 and 5 would be the answer for that one. In terms of reactivity, I would know that Pyrrol is the most reactive.
Most reactive out of the heterocycles?
Out of the pentadiene, the heterocycle pentadienes. So it goes Pyrrol, furan, and then thiopene? Phene.
Some remember.
Okay. So when we're talking about pyridine, okay, again, you should know where this attack would take place. So if I put my arrows here, what number of carbons are those?
2 and 5? No,
Say
2
2 and 5. No, 3. Wait.
2 and 4.
Where do I start
2
numbering?
and 4.
You start numbering at N.
At N, right, okay, there we
So
go.
1, 2, 3.
2, 3, 4, and 5.
Okay.
So 3 and 5, okay? But again, the more important answer to that is, where do you start numbering, right? As long as you know where you start numbering, it's always going to be on the hetero atom. You'll get the number. But again, so pyridine, 3 and 5. Does pyridine undergo EAS more readily or NAS? NAS, right. So this really doesn't happen very often. EAS of pyridine only occurs under extreme conditions, okay? When we look at NAS of pyridine, what's the common name for this reaction?
The Chi-Chi powder.
Yes. It's a fun name. Okay, so again, in terms of locations of reaction,
So do these reactions always happen on the carbons adjacent to the heterocycle atom?
no, because if we look back here, right, we've got carbons 3 and 5, right? So, yeah, again, a blanket statement there isn't easy. For NAS, you do have them on the adjacent carbon atoms, but you also have it on the one on the other side. So we've got 2, 4, and 6 here if you're trying to remember numbers. 2 and 5, 3 and 5, 2, 4, and 6. Okay. Why does pyridine undergo NAS more readily than EAS? What's the reason for that?
Pyridine's ring is all very electron poor, so the nucleophile is more attracted to it.
Exactly, yeah. Very good. Does that make sense?
Mm-hmm.
Okay.
That's right.
All right. The only other reaction here is the Paul-Moore synthesis. I don't know if this was one that he focused on a lot, but essentially we have a dicarbonyl compound, and it's being converted into a heterocycle pentadiene. That's what I would know about it.
Can you repeat that?
Yep. So you have a dicarbonyl compound, so something with 2 carbonyl groups, and it's a ring closure, okay, and it's being converted into a heterocycle pentadiene. And that could be, again, with a nitrogen, oxygen, or a sulfur. Any questions on those reactions? Okay. Okay, so we talked a little bit about pyridine. Now let's fuse pyridine and benzene. So here we have our benzene ring. Is the benzene ring considered electron rich or electron poor? Electron rich. Okay, we just talked about the fact that pyridine is electron poor. Okay, so when you have these two fused together, this is called quinoline, which I don't think he asked you any questions on your quiz about.
We had one where we had to write in the placement of EAS, NAS.
Oh, okay. So that's what I would recommend knowing anyway. So good. So where would you expect and we can just base it on the ring. You don't have to pick an actual carbon. But which ring would you expect to have react in an EAS?
Benzene.
Benzene. So I barely see them, but those would be the 2 sites of EAS. And then we would expect NAS to be here, the one that is adjacent to nitrogen, yes.
So my question is, what's the reason for only one location for nucleophilic attack?
That's a good question. I'm wondering if it might have something to do with steric hindrance.
Okay.
That would be my guess. I don't know that for sure, but considering the proximity of these 2 groups,
Okay.
And nucleophiles tend to be larger than electrophiles, so that would be my guess. You guys also talked about isoquinoline. Isoquinoline is just an isomer where the nitrogen has switched places.
Yeah.
So if you have isoquinoline, this would be your site of attack, which, again, I don't know why in this case it works here, but not here.
Isoquinoline obviously looks like it makes more sense why it'd be one spot, but the
Not sure why
Okay.
in that case. That would be a good Dr. Fred question. I'm sure there's a reason for that. Okay, so that's quinoline and isoquinoline. Again, really just focusing on knowing which one's electron rich, which one's electron poor, and what that means for the reaction. There were quite a few questions from what I could remember people saying about these this last piece. So indole, azabenzenes, pterins. I don't know if I'm saying that right. Trying to remember the question on indole. I don't think it had to do with...
I think for the quiz that we had, he just asked, what is the structure?
Okay.
I don't know about the exam.
Okay. Yeah. I mean, I don't think you would have to know the exact... I don't think you should learn how to draw indole. I don't think that would be something he'd ask you. But I would know that it contains nitrogen. It's essentially a benzene and a pyrrole. So you've got Again, I don't think the structure is necessarily important, but benzene and pyrrole. I mean, Dr. Cosper's notes mentions that it's found in certain amino acids. I don't know if that's necessarily something he focused on. Okay, so then azabenzenes and pterin. So I think the piece that confused some people, so these were mentioned one right after another. Azabenzenes, very easily synthesized in the lab. Pterins are not easily, so they are naturally occurring, but they're not easily synthesized. Which I think was kind of his question. I think he mentioned specific. It was like xanthopterin or something along those lines. And I remember somebody was asking a question about it. But anything that ends in this, you should know that it's naturally occurring, but it's not easily synthesized in the lab. Okay? Dr. Cosper's notes mentions the Hantz pyridine synthesis, but it didn't sound like that was a focus on your quiz, or really in Dr. Fred's notes from what I could tell. So I think what we went over, those tended to be his bigger focuses.
This is pretty much all that we talked about, was that it was green, there wasn't any like trash products at the end.
Right,
and
right. Yeah.
That was really all he
Yeah.
said.
And so I would just continue to link that as being a green reaction. But moving on to chapter 26. I do know that there was a lot of information in Dr. Fred's notes. I think this was a pretty long set of notes to begin with. So we'll go through Dr. Cosper's notes, but I know that there are topics that he discussed in detail in his notes, so we can go over those. Okay, so let's start with amino acids.
Was there anything in chapter 25 that you noticed were in his notes that weren't in Cosper's? Because that's what he wrote, that the majority is going to be. We have 25 questions from chapter 25.
I have a feeling that a lot of that's going to be structure. That I can't say that for sure, but I have this inkling of a feeling that that's what's going to be. I can't see how he can get 25 questions out
That's
of
what I
chapter
was
25.
saying. Like, that didn't seem like enough material.
I'm trying to think. Amber, do you recall anything?
Um,
Because we went through chapter 25 2 weeks ago. But I don't remember there being any information.
I know he talked about azanaphylanes. He talked
Yep.
about NAD converted to NADH.
Right, okay. We can talk about that.
And then just how the Hantz reaction is a pyridine condensation.
Okay. So let's take a second then to talk about NAD. So that was the chapter that he talked about nicotine then? Because NAD
Yes.
is related to nicotine.
Yeah.
Okay. All right, it's coming back to me now. Okay, so NAD, you don't need to know the long name for it. I don't know it off the top of my head. It's related to nicotine. It is an important structure as it relates to metabolism. So some of you might remember from biology when you're talking about glycolysis or the electron transport chain. Okay, so NAD is a it helps to oxidize the fuel. Okay, so when we're metabolizing fuel, so say like glucose, we're metabolizing glucose. We're oxidizing glucose to get the energy from it, okay? So whenever you oxidize something, something else has to be reduced. So this NAD, and also, I'll put it to the side because we don't have to talk about it, but FAD, you can't even see it, so it doesn't matter. NAD and FAD play a really important role because they take the electrons, they become reduced, and they allow the fuel to be oxidized. So when that happens, NAD is converted into, NAD plus is converted into NADH. Okay? So we've accepted the electrons from the fuel, we've become more reduced, Essentially, all of these NADHs and FADH2s then go to the electron transport chain, and we actually get the majority of our energy from the transfer of those electrons to the electron transport chain. So I would know that it's related to metabolism, and it's important in oxidizing fuel. I don't remember anybody asking me, there was a question on the quiz, I don't think so, but it is up for grabs. And I think the reason that it came up is because it is related to nicotine, and you did a whole thing on nicotine and nicotine supplements. Okay.
Yeah. When we talked about alkaloids, he talked about
That's
all
not
the
been there
drugs.
because I do not remember that.
I know in his notes he mentioned, so they make like the nicotine gum, right, for people to quit smoking. And he was making the argument that that's really not an effective way because then the people just get hooked to the nicotine gum, so you're not really making them quit anything. And the drug that they use for that is not, it wouldn't be considered a green synthesis. You end up basically losing 2/3 of your starting material just to make, a small amount of that. So he spent a lot of time talking about that, I think.
Yeah.
But,
And they both promote cancer, the
yes.
drug and the nicotine.
Yes, so not ideal either way.
This 26.
Yes.
Yes. You can't tell I'm writing amino acid.
Can't
Really?
even see that, to be honest. I got a
No
glare,
way.
Yeah, so-
and a light colored marker.
Okay, amino acids. So when we're talking about amino acids, it sounds like one important thing that he wants you to know is their structure, okay? So amino acids have certain characteristics that are the same throughout and one that differs based on that amino acid. So we have our alpha carbon. Oh my goodness.
There's markers in that room.
They took my markers? That's why I couldn't find them.
To draw a horse. Like an elaborate drawing of a horse on the board.
I can see it.
I could not believe I couldn't find them. That's why. Okay.
Yeah, we could really start.
Okay.
Maybe we can really get down to business. Maybe.
Oh wow, look at
there we
that.
go.
Okay. All right, so we have our alpha carbon. We have an amino group. We have a carboxylic acid group. And we have a hydrogen. Okay. So these components are the same throughout, okay? The only thing that differs is our R group. So this is what differentiates one amino acid from another. You should probably at least know the 4 categories of amino acids. Do you guys recall that from lecture?
Polar,
Okay,
non-polar,
Yep.
acidic and basic.
good. So every amino acid falls under one of those categories. I don't believe that he's going to have you identify the category, but we can just review that so you're ready for it. For nonpolar is usually the easiest one to pick out as long as you remember that hydrocarbons are polar, right? So if it's just carbons and hydrogens in your R group, it's going to fall under nonpolar. The rest of them have at least one polar bond, okay? Acidic and basic are special in that their R group has a charge, okay? So acidic are going to have a negative charge. Basic is going to have a positive charge. I want to be clear that that is going to happen in the R group, okay? One thing about amino acids, both the amino group and the carboxylic acid group can become ionized. So when that happens, our amino group will have a positive charge on one end, and our carboxylic acid group will have a negative charge. Do not get these charges confused with a charge on your R group. Acidic and basic are referring to the R group. Any amino acid could have an ionized amino or carboxylic acid terminal.
So all the classifications come from the
Just
R
from
group.
the R group, exactly.
Okay.
What's an example of a non-polar one? R group?
Anything that's a carbo,
Hydrocarbon.
yep,
Just C's and H's.
Just
Yep.
hydrocarbon.
Method.
Okay.
the only one that is not just carbons and hydrogens, you've got something like this. I don't think that's the exact structure. There's another carbon in there, but I can't think of it. So yes, we have a sulfur, which we know is a more electronegative atom. But because we have two nearly similar polar bonds, and their geometry is opposite of each other, they cancel each other out, okay? It's just like when we have a carbon that has 4 of the same bond. All those bonds are polar, but because they are opposite of each other, they cancel each other out. So this would be the only one that I would be careful of. It trips me up sometimes because I see the sulfur and I just think polar.
So that's non-polar.
This is non-polar.
Okay.
Everything else only has carbons or hydrogens.
So polar would be anything with an electronegative group unless it cancels out.
Yep, and it doesn't have a charge. So be careful because, so for example, I think this one's lysine. So lysine has a nitrogen carbon bond, so it's polar, but because it has a positive charge, it's considered basic. Okay? These are really easy to pick out, right, because they have a charge on them. Non-polars, only carbons and hydrogens. Everything else, if it has a polar atom other than this instance, it's polar. So for example, we might have something like, okay, no
So-
charge, oxygen, yep.
Okay, polar, no charge, electronegative group.
Yep.
Okay.
Again, I don't even know
It
if they'll have you
doesn't
do
fit
this.
into the last three. It's polar.
Exactly.
Okay.
It's a great way of thinking of it.
R group.
Again, it's a long shot as to whether he'll have you do this, but he may, so at least you know now.
There's a lot of questions on 26, he said.
Yeah, I mean, you didn't have a quiz on it, so he wants to make sure that he's at least quizzing you on the material. Okay,
On file.
yes. Let's see here.
What?
There's a lot of reactions. That's all
Yeah, I know.
in every chapter.
Yeah. So amino acids are considered chiral, okay? And that's because they have usually 4 different attachments. There is one that has an H as its R group. Why would this one not be considered chiral?
Because the H's cancel
Yes, so there's a form of symmetry.
Yeah,
Okay, right, so chirality is asymmetrical, okay? But if you have a form of symmetry, that makes it achiral, okay? So all other amino acids other than this one, which is glycine, are chiral. And just like sugars, we can have D or L isomers, okay? Now, when we're talking about sugars, which one occurs more readily in nature?
D.
D. Amino acids, it's the opposite. Okay, so amino acids, L is the more common one in nature. So I've drawn here an amino acid that's been ionized, okay? There is a term that you've used before. I don't know if it's been this semester or not. If an atom can have 2 different charges on it, what is that referred to as?
Swear ion?
Yes. So a zwitterion is just something that can have two charges on the same molecule. And because of these two different functional groups, amino acids are considered acidic and basic. What's the term for that if something's acidic and basic? Mhm. So these are definitely terms that you should be ready for. I think a lot of this is gonna be fill in the blank.
So, like,
Yeah.
for post-translational modifications,
Yeah.
what is that?
What is that? Okay, yeah.
Oh, I know this from biology.
It's been a hot minute since I took bio.
Mhm. I'm trying to think of how you would need to know it for this class.
Yeah.
Honestly, he probably won't use a question for this one. I feel like it would be a difficult one to ask.
Isn't that like? I'm trying to think of how to explain it. It's like when a modification happens to the DNA to like make something that doesn't readily occur.
So it wouldn't be happening to the DNA. This is happening to amino acids. So you can have amino acids. So imagine in your cell you have amino acids flowing around all the time, okay? So essentially what this is saying is that specific modifications can be made to the amino acid, okay? And this can be done, so translation is just referring to the turning of mRNA to protein. So basically after that process is complete, there can be different modifications that are added to that. And he gives a list.
Okay, so it could be like disulfide bridges, alkylation,
Yes,
nitration.
yes, all of those are different
those-
types.
Okay, got it.
I feel like if he were going to ask you a question, he might be like, give me an example of post-translation modification.
What would that answer be?
There is a nice little list in Dr.
Yes.
Cosper's notes. I think the easiest one, and we'll talk about it so it makes a little bit more sense, disulfide bridge formation is an easy one. We'll talk about that one when the folding.
Yeah, because we talked about a few of those already. So.
Can
Yeah.
we talk about like when we go through all these too? Can we do like examples of each? Because I feel like he's big on asking for examples.
Yeah,
More.
I'll definitely show you examples for the different types of protein folding. Definitely.
Yeah.
Yeah, okay. Good questions. Okay. So, because these are chiral, our D and L isomers are considered enantiomers of each other, right? So, what is it called when we have a mixture with 50% D and 50% L?
Receiving.
Racemic mixture. How would we get, what process would we use to convert that racemic mixture into just L isomers? Resolution, okay? So this is stuff coming back up again, right?
But
So,
that's not likely to happen though. It's like super slow, right?
I'm sorry, what?
Isn't like
resolution?
resolution for that amino acid going to be super difficult?
I don't know for sure. He may have mentioned something. I've never done it before, so I can't speak to that. Could be. But those terms, you might see them again, so just make sure that you remember those. Okay, so now let's talk about when we link some of these amino acids together. So what are amino acids the building block of?
Proteins.
Okay. What's the difference between a protein and a peptide?
Peptides are the building blocks, and the protein are.
Proteins are change of peptides, aren't they?
Yeah.
Okay, okay, close. So it's really just size. Peptides and proteins are really the same exact thing. It's just peptides are smaller.
Amino acids are the building blocks.
Okay, so a small chain of amino acids is a peptide, but when we get into larger chains or multi-chain structures, that's when we're talking about proteins. All right, so if I many amino acids do I have here?
Three.
3. Okay. How do we identify that there's 3? How do you know?
That's
They repeat. Yeah.
There's 3 hydrogens on the bottom.
3 hydrogens on the
That's
bottom.
how I found
Okay,
it.
okay, I like it.
Each
Yes.
system repeats.
Okay,
At
great.
the carbon
Like the one.
Yeah, yeah. So I like
or
to
after the carbon.
look at the backbone, okay? And I look for NCC, 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 because we know that every amino acid is going to have NCC in it, okay? So NCC, 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 okay? So that's my favorite indicator. Not saying that yours won't work as well. I'd be careful with the 3 hydrogens on the bottom.
No, that's just how I found like my middle point.
Got it.
of
Okay,
the-
okay. Because he could always write it like that. You know, the
Yeah.
structure wise could change slightly. But yeah. So find your alpha carbon. Find whatever you need to find. He could ask you something along these lines. Okay. What are the bonds that link amino acids called?
Peptide bonds.
Peptide bonds. Excellent. So amino acids are the Legos linked by peptide bonds to make peptides and proteins. Okay. Why don't we practice classifying these amino acids? Okay. So I want you to tell me whether this amino acid is polar, nonpolar, acidic, or basic.
Non-polar.
Okay. Nonpolar, right? Because we've got carbons and hydrogens. There's nothing else here. Okay. So nonpolar. What do we got here?
Polar.
Polar. And I kind of already showed you guys this one, but
Non-polar.
so this is the one that I was referring to. Because we have those 2 polar bonds, this one is also going to be considered nonpolar. Okay. Again, some terminology. He may want you to identify the N terminal or the amino terminal. That's just the side that ends in N. Or he might say the carboxy terminal or the C terminal. That just ends in C. Yes.
Off of Cosper's notes,
Yes.
the amino sequence at the bottom with the benzene ring in that,
With the
Would-
alcohol,
yeah.
the phenol.
Oh,
Would
I
that
had
be-
an OH on it. Yeah.
Would that be polar?
It would be polar, yes.
Okay. Because of the O.
Yes, that O would do it.
Okay. Thank you.
Mm-hmm. The backbone, okay, if he asks you to identify the backbone, you're going to basically circle everything other than your R groups, okay? So just as an example, I don't know if this is something he would do. Your backbone in this case would be that, okay? Usually, generally, you can kind of just go like this and say backbone and side chains, right, like Dr. Prosper has it, but just for a visual. The backbone, that's what he's referring to, side chains. Another term that he might use is residue, okay, so this is considered a residue. This is your R group, this is your residue, okay, so just another term for an amino acid,
So
residue.
the residue doesn't include the R group?
It does.
Oh, okay.
It does. It's the whole amino acid. Okay, but the R group, you sometimes R residue you can get a little confusing, but
Oh, okay.
okay. Do you want to go into protein folding? Okay. So essentially, there are 4 possible types of protein folding. Dr. Cosper's notes kind of skips over the first one, but it's kind of what's discussed here. So we have primary. And primary is just the list, or the primary structure is just the list of amino acids. So if I just gave you the name of each amino acid in a row, that would be the primary structure. Secondary structure is actually, there are 2 different kinds, okay? So you have alpha helices and beta sheets, or beta pleated sheets, you might have heard them referred as. Secondary structure is referring to a short piece of your amino acid chain, okay? So if we were looking at so if this was our primary structure, right, just a list, our secondary structure might be, you know, we have an alpha helice here, and then we have a beta pleated sheet. So a small portion of that chain has some sort of structure to it, a helice or a sheet.
It doesn't have both though, right?
You can
You
have,
can have both.
not in the same piece. You can have two, you can have them in the same chain,
Okay.
but not the same section.
Okay.
Like you can't have a helice
One on top
and
of each other.
yeah. Oftentimes, I can't say all the time, but almost always you have both in a protein.
They can be right next to each other.
I don't know how close they can be together. I don't know for sure. Okay. So we're talking about small pieces of the chain. Tertiary is when we get into looking at the 3D structure as a whole. Okay, so we're no longer just looking at a short piece of the chain. We're looking at the chain as a whole and how it's interacting and folding. So there are different types of 3D structure. Dr. Cosper doesn't go into detail in her notes, but I know Dr. Fred does, so we can talk about them. So we have, let's see, I'll do it this way. So we have ionic, hydrogen bonding, nonpolar, disulfide. Those are the four that I can think of. I think those are the four that he talked about.
Hydrophobic.
Oh, nonpolar. All right, hydrophobic. Was there just four? Was there another one, Amber?
Disulfide, ionic, hydrophobic, and hydrogen bonding.
Okay, yep. So those are the four you should know. So secondary structure has to do with the backbone interacting. Okay, so you have hydrogen bonds of the backbone that leads to this type of structure. 3D structure has to do with the residues. So, sorry, not the residues. See, I did it, the R groups. So the R groups are interacting with each other, and that's what creates the more complex folding. So ionic is when you have acidic and basic amino acids coming together, right? So you have a positive and negative charge. So that's going to create an ionic bond. Hydrogen bonding, you should already be pretty familiar with, right? So something that has an OH group, like the amino acid that we just looked at in Dr. Cosper's notes. So that OH group might be attracted to another residue that has an OH group or a nitrogen or something along those lines. Hydrophobic is really important. This is what drives a lot of the folding. So basically all of those non-polar amino acids, and there's a lot of them, that's actually the biggest group, they're not going to want to be on the surface of the protein, right? Because the surface is touching water. So all of the hydrophobic proteins are going to orient themselves towards the inside of the protein. So that causes that affects a lot of the folding. And then disulfide bridges we talked briefly about for post-translation modifications. So basically you have two cysteine amino acids. So if we have okay, so the cysteine has this SH, this thiol group. Basically, the hydrogens are removed and we create this linkage here. So you can see where the name comes from. Disulfide, two sulfurs, bridging the gap.
So you lose a hydrogen?
Yeah, each of those groups are going to lose a hydrogen to form that bond. So again, 3D structure, we're looking at the folding of the whole protein. Different interactions among your R groups are going to affect this, and I would know the 4 different groups. I would know that disulfide involves cysteine amino acids. CYS is the 3-letter code for that. Okay. Yes, sorry.
I don't know if you're gonna go over it, but do you think he'll go into quaternary structure?
Yeah, we're going to talk about quaternary.
Okay, yeah.
So up until this point, every level of structure, every protein has. So you could look at any protein, and it would have primary, secondary, and tertiary structure. Okay? However, once we get into quaternary structure, only some proteins have quaternary structure. So quaternary, we're looking at how multiple chains are coming together. So you have multiple subunits. I know he spent some time talking about myoglobin and hemoglobin, and this is a perfect example of that. So myoglobin, well, hemoglobin, we know is found in the blood. It's used for the transportation of oxygen from the lungs to the muscles, the tissues. Myoglobin is a very analogous structure, but it's only found in muscle, muscle. But it also helps store oxygen, etc. So when we're looking at myoglobin, myoglobin is a single chain protein. So it would have primary, secondary, and tertiary structure, but it would not have quaternary because there's only one chain that makes up that protein. Hemoglobin, on the other hand, has 4 different subunits. So 4 different protein chains come together to make one protein. So that means it has all 4 levels of protein structure.
So myoglobin is tertiary structure? Is that what
Has primary, secondary, and tertiary, but
But-
not quaternary.
Okay.
Okay.
So it's just one protein, or is it? not
Yep, just one chain. I think that's a better way of thinking of it.
So the way of classifying quaternary structure is multiple chains.
Yes,
So myoglobin is not a quaternary structure.
exactly.
But what's it a chain of? I
So
think
an
that's why
amino acid chain. So right, so we've been talking about proteins, right? So I'm talking about one chain folding to make a protein. But some proteins require multiple chains. So you have one chain
Oh,
of amino acids,
yeah.
and then this has to somehow interact to link up with this chain, and then this chain,
When you look at hemoglobin, it's a
And
whole
this
mess.
yeah.
Like just literally.
So we have 4 different subunits, and actually with hemoglobin, you have 2 different types. So you have 2 alpha, 2 beta. So we have 4 different subunits, 4 different separate amino acid chains that are coming together and interacting with each other to create a fully functional protein.
Okay. So hemoglobin is a protein.
Yes,
Okay.
hemoglobin and myoglobin are proteins.
And the difference between a protein and a peptide is a peptide just has smaller amounts of
Yep.
amino acid chains.
Yep. Remember when we talked about sugars and like there's oligosaccharide and then polysaccharide?
Yeah.
It's basically the same thing.
Okay.
Oligosaccharide is like a few, polysaccharide is many, but like
Yeah.
what's the cutoff between an oligosaccharide and a polysaccharide? Yeah.
Okay.
Semantics.
Can you go over like the equation thing he did of how to find how many
Oh,
different,
okay. Yeah,
like there's 20 amino acids and
you're right.
find,
Where did he put that?
That was,
I feel like you like touched on it quick, but I feel like
yeah,
that's, he's gonna ask
that was
us
like
this.
Okay.
1600 and 3200.
Yeah.
Yeah, something like that, yeah.
So I would be careful because so we'll go over with what he said, but he might use different numbers. The 20 will stay the same, but the 3 will be different. That might be different. Okay. So basically he's saying there are 20 known amino acids. Okay, and he was asking about a trimer. How many amino acids do you think are in a trimer?
3.
Yeah. So basically, he was asking about the number of unique sequences. And I think technically with his calculation, order doesn't matter, but we're not going to focus on that. But basically, you're going to take your number of amino acids, or your options, and you're going to raise it to the number of slots that you have.
Okay.
Okay, so it's 20 to the 3. Basically, if you think of it like you have 3 different slots, right? And the first one, you could have one of 20 different amino acids in it. So you have 20 different options for slot 1. The second, you have 20 different options for slot 2, 20 for slot 3. So 20 times 20 times 20, 20 to the 3rd. So depending on how long he wants the chain to be, that's what you would raise
That's the
it
next
to.
one. Okay.
Yep. Does that make sense?
Mm-hmm.
Okay. Okay. I don't know if he didn't really focus on the process of Edman degradation. I do think you should know what it is. So basically, in the early times of determining your primary structure, right? So trying to determine what your sequence of amino acid is. The Edman degradation was a process that was commonly used. It does have a lot of limitations. It's pretty tedious. You can really only do, I think it's like up to 50 amino acids. Once you get any larger than that, it just becomes a pretty painstaking process. They really don't use it very much anymore because we have more sophisticated techniques. We usually determine the DNA sequence and then work our way forward instead of working our way backward. But Edman degradation, I know he did mention it in the notes. He didn't focus on the process of it. Like there weren't any details in his notes either.
So we just need to know it's going to
Perfect.
tell us which amino acids are.
Yeah.
Are they?
Yep. It's just the sequence. Exactly. Okay. So now I'm moving into nucleic acids. Any questions about proteins or amino acids?
Nope.
Okay. How am I doing on time? Anybody gotta watch
It's 2:40.
It's 2:40.
already?
Yeah.
That's an hour, isn't it?
Yeah.
Okay. All right. That's a bummer.
Holy moly.
Let me just check my schedule. I know I have something else, but I don't remember what time it is.
I feel like we've been down here for 15 minutes.
I
That's
know.
It
ridiculous.
doesn't feel like that long. Yeah, I'm just staying up all night. For the next 2 nights.
When are you taking it?
Wednesday morning.
Same.
Taking it tomorrow morning.
I couldn't.
You got this.
I do have 2 peer tutor evals, but I don't have. Let me just
They can wait.
before I say. Could you guys hang out for 20 minutes? Because my
Yeah.
last thing would end at 3.
You can hang out as long as you
Okay.
need us to.
And then I can give you another hour or so, if that's okay.
Yeah, that's totally